So this is a case study of sports engineering, conducted by students at the University of Georgia's College of Engineering. Specifically, we're going to be discussing the coefficient of restitution and its application to sports. So the coefficient of restitution was first described mathematically by Isaac Newton in 1687 as a way to relate final and initial velocity and heights between objects when they collide. It can also be found by analyzing energy, kinetic energy, before and after the collision. The purpose of our research is to accurately replicate sports engineers' testing methods for various sporting objects' coefficients of restitution and subsequently analyze our data by comparing experimental results to theoretical ones in hopes of suggesting guidelines for the use of materials and design methods based on desired sporting outcomes. So our experiment method was simple. We placed a ruler on a wall and dropped spherical sporting objects from a certain height distance and filmed their motion using a program called Tracker using a HD Canon camera. This tracker program will analyze it and give it a resulting velocity and height differences between the ball before and after collision, which will be used to calculate the coefficient of restitution. The governing equations we used were derived from the conservation of energy and conservation of linear momentum. Combined, this gives you the coefficient of restitution for both the ratio of velocities and the ratio of heights. The only condition to consider is that we're looking for a coefficient of restitution between 0 and 1, which is a real-world inelastic collision. The predictable experimental variables that we're looking to limit are the bouncing angle and the frame rate of the camera. This will cause error in our experiment and will most likely result in a less coefficient of restitution than we desire. So in order to collect our data, we had a team member drop the balls from a certain distance. Here we can see Justin dropping a golf ball, and as the ball falls to the ground, the tracker program will track its motion. On the right side of your screen, the motion will be tabulated in graphs on both velocity and height, velocity being the bottom one. Another thing to note is as the golf ball bounces 2 or 3 times, you can see it deviating from its original vertical path. By tabulating this data, you can see the differences between the different ball types. On the left we have basketball, to the right we have tennis. The difference between height differences are noted by these apexes, where the difference in velocity are noted by the top and the bottom on each bounce. Comparing these values and calculating the coefficient of restitution using those values to the desired values, we can see that the formula for height gave only a percent error of 3.75 and 3.53, whereas the 3 other experiments fell within the range of desired. So our experiment was conducted very well using the height formula. However, using the velocity formula, we had 4 that lie outside the range of desired coefficient of restitution. This is most likely contributed to a low rate of frame for the camera, which can't capture the velocity quite as accurate. So while the soccer ball was only slightly deflated, it did not perform within the desired limits by either the velocity or the height test. So what this tells us is that by changing the conditions even slightly, it can change the coefficient of restitution greatly. This will help inform us for recommendations. Another thing to consider is that the surface material and object material is different. So the racquetball and tennis ball are very similar ball types, but their material is different, which contributes to a different coefficient of restitution. Some errors from this is, like we thought, the angle theta from the original line to the line of third bounce can be quite great, which can contribute to rotational energy, which we're not looking for when trying to calculate coefficient of restitution. So important design factors to consider. When designing for a specified coefficient of restitution, the object's overall elasticity contributes the most. So if you're looking for a high coefficient of restitution, you want high elasticity in your material properties. So how can it change the game, per se? Well, if you're playing basketball, you don't want to use a bouncy ball because the ball will have a rebound effect too high for what you're looking for. So it's important to consider how you're wanting the ball to behave when designing. So engineers should play an active role in governing sports bodies to inform officials how external conditions can alter a sporting ball's behavior. By doing this, officials will be able to ensure that playing conditions are constant. So this can be done in certain intervals during a game or match by simple drop tests to ensure that the ball's coefficient of restitution is consistent with desired values. And as we saw, a slight change in condition can have a pretty high effect on the change of coefficient of restitution, so that should be monitored fairly closely during a game. Thank you.